The closest star to our Sun is so far away that if you could drive there at highway speed, it would take you 48 million years. Alpha Centauri, our nearest stellar neighbour, sits 4.37 light-years from Earth, a distance so vast it challenges every human understanding of space and time. Tonight we'll journey step by step into this cosmic measurement, using real data from ESA's Gaia mission, the physics of light itself, and the ingenious methods astronomers use to map our stellar neighbourhood. We'll discover why this distance represents both an impossible gulf and an intimate closeness in the grand scale of our galaxy. It's a story of parallax shifts, stellar motion, and the patient work of measuring infinity itself, quiet, precise, and humbling. If this gentle exploration sparks your curiosity, your soft like or quiet subscribe would mean the world to me. These cosmic measurements become so much more meaningful when shared. Now, close your eyes. Let's drift toward our nearest star. What happens when your eyes deceive you about the most fundamental truth of our universe? Tonight, as you lie down and gaze toward the southern sky, Alpha Centauri appears as a single bright point suspended in the cosmic darkness, a gentle beacon in the constellation Centaurus that seems close enough to touch if you could just reach a little farther into the night. This luminous dot presents itself with such deceptive simplicity that your mind naturally assumes it belongs to the same celestial neighbourhood as every other star scattered across the heavens above. To your eyes, this stellar neighbour differs little from stars that are thousands of light-years away, creating a perfect illusion that all these distant suns exist on the same cosmic canvas, painted at equal distances across the dome of night. But what if everything you perceive about stellar distances is fundamentally wrong? The night sky performs its greatest magic trick every evening, flattening three-dimensional space into a two-dimensional tapestry that masks the true nature of cosmic architecture. Alpha Centauri holds secrets that reveal how our universe operates on scales so vast they challenge every intuition we possess about space and distance. When ancient astronomers first catalogued this southern star, they placed it among the brightest points of light visible to the naked eye, never imagining that what appeared as one star was actually three separate worlds locked in an eternal cosmic dance. The human eye evolved to navigate terrestrial landscapes where distant objects appear smaller and dimmer, fails completely when applied to stellar observations where brightness depends on both distance and intrinsic luminosity. A nearby red dwarf can appear fainter than a distant blue giant, creating visual paradoxes that confused astronomers for millennia. Alpha Centauri masquerades as a single entity while harbouring multiple stellar components, each with its own story of nuclear fusion, gravitational mechanics, and orbital dynamics. What appears as one star is actually three separate worlds existing in a complex gravitational ballet that has persisted for billions of years. The primary components, designated Alpha Centauri A and B, orbit each other in an elliptical dance that takes nearly 80 years to complete, their separation varying from 11 to 35 astronomical units as they swing closer together than Neptune orbits our Sun, then retreat to distances greater than the orbit of Pluto. Meanwhile, Proxima Centauri, a red dwarf star barely visible even through powerful telescopes, circles this stellar pair at a distance of 13,000 astronomical units, like a distant moon orbiting a double planet in slow motion across cosmic time. Even in this supposedly close system, the components are separated by distances that dwarf our entire solar system, revealing how the word close loses all meaning when we step beyond our planetary home. The constellation Centaurus stretches across southern skies like a cosmic centaur frozen in stellar fire, with Alpha Centauri marking the position of one bright foot, yet this mythological creature spans angular distances that translate to incomprehensible physical scales. Every point of light you see scattered across this constellation exists at wildly different distances from Earth, some relatively nearby at tens of light-years, others lurking thousands of light-years deep in space, creating a false sense of cosmic organization where none actually exists. Your perception naturally groups these stars into recognizable patterns because human brains excel at pattern recognition, but the universe cares nothing for our need to organize celestial chaos into meaningful shapes. The southern hemisphere provides the clearest view of Alpha Centauri, allowing observers in places like Australia, South Africa, and Chile to witness this stellar system throughout the year as Earth rotates on its axis and orbits around the Sun. Northern Hemisphere observers must content themselves with occasional glimpses near the southern horizon during spring months, and even then only from locations south of latitude 40 degrees north. This geographical limitation meant that many classical astronomers in Europe and Northern Asia never observed Alpha Centauri directly, relying instead on reports from travellers and Southern Hemisphere observers to understand the nature of this important stellar system. The brightness of Alpha Centauri results from the combined light of both primary components, Alpha Centauri A and B, whose individual luminosities blend together to create what appears to be a single brilliant star with an apparent magnitude of -0.27, making it the third brightest star in our entire sky after Sirius and Canopus. This remarkable brilliance led ancient civilizations to incorporate Alpha Centauri into their mythologies and navigation systems, using its position to mark seasons and guide travellers across vast terrestrial distances, never suspecting that the star itself resided at a distance that would make even the fastest spacecraft journey last thousands of human lifetimes. Could you imagine discovering that what appears to be a single point of light actually contains multiple hidden worlds performing an intricate gravitational ballet across cosmic time? What appears as one star is actually three separate worlds locked in an eternal cosmic dance that has continued for billions of years, each component following precisely calculated orbital paths determined by the fundamental laws of physics that govern all matter in our universe. Alpha Centauri A and B, two sun-like stars with masses and temperatures remarkably similar to our own solar furnace, will orbit each other every 79.91 years in an elliptical embrace that demonstrates how gravity sculpts the architecture of stellar systems across the galaxy. Their separation varies dramatically throughout this orbital cycle, swinging from 11 astronomical units at their closest approach to 35 astronomical units at maximum separation, distances that place them alternately closer together than Saturn orbits our Sun, then farther apart than Neptune completes its frozen circuit around our solar system. This variation creates a constantly changing gravitational environment where each star influences the other through tidal forces, stellar winds, and magnetic field interactions that produce observable effects detectable by modern astronomical instruments. The primary component, Alpha Centauri A, burns slightly brighter and hotter than our Sun with a mass roughly 10% greater, while its companion Alpha Centauri B glows with cooler temperatures and dimmer luminosity, possessing approximately 90% of our solar mass, yet maintaining surface temperatures several hundred degrees lower than the star that warms our planet. These stellar twins formed from the same primordial cloud of gas and dust approximately 4.8 billion years ago, condensing under their mutual gravitational attraction until nuclear fusion ignited in their cores, transforming them into the mature main sequence stars we observe today. The orbital mechanics governing their dance follow Kepler's laws with mathematical precision, their elliptical paths traced through space with such regularity that astronomers can predict their positions centuries into the future or calculate their arrangements millennia into the past. But this binary system harbours an additional secret that remained hidden until relatively recent astronomical surveys revealed the presence of Proxima Centauri, a red dwarf star that circles this stellar pair at the enormous distance of 13,000 astronomical units, like a distant moon orbiting a double planet in slow motion across cosmic epochs. Proxima Centauri completes one orbit around the Alpha Centauri AB, barycenter every 547,000 years, a time span that encompasses hundreds of human civilizations and geological epochs on Earth. This third component burned with the dim red glow characteristic of low-mass stars, possessing only 12% of our solar mass, yet capable of maintaining nuclear fusion for trillions of years due to its efficient hydrogen consumption rate. Red dwarf stars like Proxima represent the most common stellar type in our galaxy, comprising roughly 75% of all main sequence stars, yet their faint luminosity renders them invisible to naked eye observation despite their cosmic abundance. The gravitational relationship between these three components creates a hierarchical system where the close binary pair dominates the central region, while the distant red dwarf follows a highly elliptical orbit that carries it from approximately 4,000 astronomical units at closest approach to over 12,000 astronomical units at its farthest point. Even in this supposedly close system, the components are separated by distances that dwarf our entire solar system, revealing how the concept of proximity becomes meaningless when applied to interstellar scales. The distance between Proxima Centauri and the Alpha Centauri AB pair equals roughly 430 times the radius of Neptune's orbit, a separation so vast that light requires nearly 2 days to travel between these gravitationally bound companions. These enormous separations demonstrate how stellar systems operate on scales that challenge human comprehension, where what we consider close neighbours actually exist in relative isolation across cosmic voids. The Alpha Centauri system provides astronomers with a perfect laboratory for studying stellar evolution, binary star interactions, and gravitational dynamics because its proximity allows detailed spectroscopic analysis of each component's atmospheric composition, rotation rates, and magnetic field strengths. Advanced telescopic observations reveal that both primary stars rotate relatively slowly compared to younger stellar objects, indicating their mature age and stable evolutionary state. The system's orientation relative to Earth permits precise measurements of orbital parameters, stellar masses, and luminosity variations that would be impossible to obtain for more distant stellar systems. Recent discoveries have identified potential planetary companions orbiting within this system, including confirmed planets around Proxima Centauri and possible worlds within the habitable zones of the primary stars, raising tantalizing questions about the potential for life in our cosmic backyard. How can something be simultaneously our closest neighbour and impossibly remote beyond all human experience? In cosmic terms, Alpha Centauri represents our next-door neighbours in the galactic suburb we call the local stellar neighbourhood. Yet this neighbour lives 25 trillion miles away, across a void so vast it renders earthly concepts of distance completely meaningless. When astronomers describe Alpha Centauri as nearby, they speak from a perspective shaped by the galactic geography where distances are measured not in kilometres or miles, but in parsecs and light years, units created specifically because conventional measurements fail catastrophically when applied to interstellar space. If our entire solar system from the Sun to the outermost reaches of the Kuiper Belt were compressed to the size of a soccer ball, Alpha Centauri would be another ball positioned 276 kilometres away, roughly the distance from New York City to Boston, or from London to the northern coast of Scotland. This analogy begins to reveal the staggering emptiness that characterises interstellar space, where even our closest stellar neighbours exist in profound isolation across cosmic deserts that dwarf any earthly comparison. The word close loses all meaning when we step beyond our planetary home and confront the reality that space itself is primarily empty vacuum punctuated by tiny islands of matter, separated by incomprehensible gulfs of nothingness. Tonight we begin to understand what distant truly means in a universe where Alpha Centauri, despite being our nearest stellar companion, remains so remote that human technology has never produced a spacecraft capable of reaching it within multiple human lifetimes. The Voyager probes, humanity's fastest and most distant ambassadors, crawl through interplanetary space at speeds that would require over 70,000 years to bridge the gap separating us from Alpha Centauri, assuming they were aimed in the correct direction and could somehow survive the journey across the interstellar medium. Modern rocket propulsion systems designed for planetary exploration operate with such limited velocity compared to interstellar distances that they represent essentially useless tools for crossing the void between star systems. Chemical rockets that can propel spacecraft to Jupiter or Saturn in mere years would need millennia to approach even our closest stellar neighbour, revealing the fundamental inadequacy of current technology for interstellar exploration. The fastest spacecraft ever launched, NASA's Parker Solar Probe, reaches maximum velocities of over 700,000 kilometers per hour as it skims the solar corona. Yet even this remarkable speed would require approximately 6,700 years to traverse the distance to Alpha Centauri. These timescales exceed the entire recorded history of human civilization, encompassing the rise and fall of empires, the development of agriculture, the invention of writing, and the entire scientific revolution that enabled us to measure stellar distances in the first place. The 25 trillion mile journey to Alpha Centauri contains more kilometers than there are seconds in 800 million years, a number so large it becomes abstract, and loses connection to human experience or intuition. Light itself, travelling at the ultimate cosmic speed limit of nearly 300,000 kilometers per second, requires 4.37 years to complete this journey, meaning that photons departing Alpha Centauri today began their voyage when global events were dramatically different from current circumstances. The light entering your eyes tonight from this stellar system carries information about conditions that existed years ago, making astronomical observation a form of time travel, where we perpetually observe the universe's past rather than its present state. Interstellar distances operate on scales that evolved long before human consciousness emerged to contemplate them, shaped by the fundamental forces of gravity and nuclear fusion that determine how matter organizes itself across cosmic space. The galaxy contains roughly 400 billion stars scattered across a disk spanning 100,000 light-years in diameter, yet the average separation between neighbouring stars amounts to several light-years, creating a cosmic architecture where stellar systems exist in relative isolation despite their enormous numbers. Alpha Centauri appears close only by comparison to other stellar distances, much like a mountain peak might seem nearby when viewed from an adjacent summit, despite being separated by valleys requiring days to cross. The Milky Way's spiral arms contain stellar nurseries where new stars form in clusters before dispersing into the galactic disk. But even these relatively dense regions maintain average stellar separations measured in light-years rather than astronomical units. Our solar system occupies a particularly sparse region of the galaxy where stellar neighbours are more widely separated than average, contributing to our cosmic loneliness and the challenges facing any attempt at interstellar communication or travel. The nearest dozen stars to our solar system all reside within approximately 12 light-years, forming a loose association of stellar systems that share similar motion through the galaxy while maintaining vast separations that prevent any significant gravitational interaction between them. Why did the greatest minds of antiquity struggle with a geometric puzzle that would torment humanity for over 2 millennia? Ancient Greek astronomers possessed remarkable mathematical sophistication and observational skills that enabled them to calculate Earth's circumference, predict eclipses, and develop complex models of planetary motion. Yet they placed stars beyond the planetary spheres, without any concrete understanding of these cosmic distances. Aristotle and his contemporaries recognized that stars must exist at greater distances than the wandering planets. But how much farther remained an unanswered question that haunted humanity for over 2,000 years, challenging every attempt to comprehend the true scale of the universe. The Greeks developed the concept of celestial spheres as crystalline shells carrying heavenly bodies in perfect circular motions around a stationary Earth, with the stellar sphere representing the outermost boundary of creation itself. This geocentric model satisfied both observational requirements and philosophical preferences for cosmic order, placing humanity at the centre of a finite universe surrounded by nested spheres that rotated with mathematical precision. However, even within this framework, thoughtful astronomers recognized that stellar distances remained completely unknown, existing somewhere beyond the sphere of Saturn in a realm of pure speculation and geometric uncertainty. Aristarchus of Samos proposed the radical idea that Earth orbited the Sun rather than serving as the centre of cosmic motion, but his heliocentric model immediately encountered a devastating observational challenge that would persist until the 19th century. If Earth truly moved around the Sun in an enormous orbit stretching across hundreds of millions of kilometres, nearby stars should appear to shift position relative to more distant background. Stars as our planet swung from one side of its orbit to the opposite extreme 6 months later. This apparent motion, known as stellar parallax, represents a fundamental geometric consequence of Earth's orbital motion that must occur if the heliocentric model accurately describes solar system architecture. The parallax effect can be demonstrated easily with terrestrial objects by closing one eye, then the other, while observing how nearby objects appear to jump relative to distant backgrounds due to the baseline separation between your pupils. Ancient astronomers understood this principle perfectly and recognized that Earth's orbital diameter provided a baseline of nearly 300 million kilometers for detecting stellar parallax. Yet this shift remained completely invisible to every observer regardless of their skill, patience, or instrumental precision. The absence of detectable parallax became a powerful argument against heliocentrism because it implied either that Earth remained stationary or that stars existed at distances so enormous they rendered parallax effects too small to measure with available technology. Critics of the heliocentric model argued that if stars were distant enough to eliminate observable parallax, the universe would be incomprehensibly vast with enormous empty spaces between Earth and the stellar sphere, a concept that violated philosophical principles favouring cosmic efficiency and divine economy. The geocentric model avoided these difficulties by maintaining Earth's central position and eliminating the need for stellar parallax, allowing stars to reside at reasonable distances on a rotating celestial sphere that carried them around a stationary planet in daily motion. This astronomical impasse persisted through the medieval period and into the Renaissance, even as improved observations and mathematical analysis strengthened support for heliocentric planetary motion. Copernicus acknowledged the parallax problem in his revolutionary treatise, but dismissed it by arguing that stellar distances were simply too large for contemporary instruments to detect the resulting angular shifts, a position that required unprecedented cosmic scales that challenged human imagination. Tycho Brahe, the greatest observational astronomer before the invention of telescopes, conducted meticulous parallax searches using instruments capable of measuring stellar positions to within a few arc-minutes, yet he failed to detect any systematic parallax effects, despite years of careful observations. This negative result convinced Tycho that the heliocentric model was incorrect, leading him to develop a hybrid system where planets orbited the Sun, while the Sun itself orbited a stationary Earth, thereby preserving some benefits of Copernican astronomy while avoiding the parallax difficulty. Galileo's telescopic discoveries provided powerful evidence supporting heliocentrism through observations of Jupiter's moons, Venus's phases, and lunar surface features, but even his improved instruments could not detect stellar parallax, leaving this fundamental prediction unconfirmed for another 2 centuries. The parallax problem highlighted the enormous difference between planetary and stellar distances, revealing that interplanetary space, though vast by human standards, represented merely a tiny fraction of the gulf separating our solar system from even the nearest stars. What technological limitations prevented humanity from unlocking one of the universe's most fundamental secrets for thousands of years? The parallax of Alpha Centauri measures precisely 0.742 arc-seconds, an angular measurement so minuscule it defies human perception and challenged the finest instruments available to astronomers for centuries after they understood the geometric principles involved in stellar distance determination. To comprehend this extraordinary smallness, imagine attempting to observe a coin from 2.3 miles away under perfect atmospheric conditions with flawless vision, because that impossible viewing scenario represents exactly 1 arc-second of angular measurement. Alpha Centauri's actual parallax shift amounts to less than 3/4 of that impossible measurement, creating an observational challenge that pushed the boundaries of human ingenuity and technological development throughout the entire history of pre-modern astronomy. For centuries, human technology simply could not detect such minute angular changes, despite the dedicated efforts of brilliant observers armed with the finest instruments their civilizations could produce. The stars kept their distance secret locked away in geometric precision that demanded measurement capabilities far beyond anything available to ancient, medieval, or early modern astronomers. Greek astronomers working with naked eye observations could achieve angular precision of approximately 1 arc-minute under ideal conditions, falling short of stellar parallax detection by factors of nearly 100 even for the closest stellar neighbours. Medieval Islamic astronomers developed sophisticated astrolabes and armillary spheres that improved measurement precision somewhat, but their instruments remained incapable of detecting angular shifts smaller than several arc-minutes. Renaissance astronomers like Tycho Brahe constructed enormous brass instruments with unprecedented mechanical precision, achieving angular measurements accurate to within 2 or 3 arc-minutes, yet this represented merely the first step toward the precision required for stellar parallax detection. The invention of telescopes in the early 17th century promised revolutionary improvements in astronomical measurement capabilities, but early refracting telescopes suffered from chromatic aberration, spherical aberration, and mechanical instabilities that actually degraded positional accuracy compared to the finest naked eye instruments. Telescope technology required nearly 2 centuries of development before achieving the optical quality and mechanical stability necessary for precise stellar position measurements. Atmospheric turbulence presented another formidable obstacle because Earth's atmosphere constantly shifts and distorts incoming starlight, creating apparent stellar motion that can exceed actual parallax effects by factors of hundreds or thousands. Even perfect instruments operated under perfect atmospheric conditions would struggle to detect parallax shifts measured in fractions of arc-seconds. The challenge resembled attempting to measure the thickness of human hair using a ruler marked only in centimeters, requiring not just improved tools, but entirely different approaches to measurement and data analysis. Stellar parallax detection demanded long-term wars. Observational campaigns spanning multiple years because the parallax effect varies sinusoidally as Earth completes its annual orbit around the Sun, reaching maximum values during specific seasons and vanishing completely at certain orbital positions. Astronomers needed to distinguish genuine parallax motion from proper motion, the actual movement of stars through space relative to the solar system, which often exceeded parallax effects and could mask or mimic the sought-after geometric shifts. Temperature variations affected instrument performance throughout the observational year, causing systematic errors that could simulate or conceal true parallax measurements. Mechanical flexure in telescope mounts and temperature-induced changes in optical components created spurious angular displacements that complicated efforts to detect authentic stellar parallax. The development of precision clockwork mechanisms enabled more accurate tracking of stellar positions over time, but achieving the mechanical tolerances required for parallax detection pushed 18th and early 19th century technology to its absolute limits. Filar micrometers attached to telescopes allowed astronomers to measure relative stellar positions with improved accuracy, but even these sophisticated devices struggled to achieve the precision demanded by stellar parallax observations. The challenge intensified because astronomers needed to measure not absolute stellar positions, but extremely small relative changes in position over extended time periods while compensating for atmospheric effects, instrumental errors, proper motion, precession, nutation, and other systematic influences. Statistical analysis methods had not yet developed sufficiently to extract tiny signals from noisy observational data, leaving astronomers without the mathematical tools necessary to confirm genuine parallax detections amid the various sources of measurement uncertainty. The technological barrier remained insurmountable until the convergence of several critical developments, including improved telescope optics, mechanically stable mounting systems, precision measurement devices, better understanding of atmospheric effects, and more sophisticated approaches to data analysis and error estimation. What fierce competition drove three brilliant astronomers on different continents to risk their careers and reputations in pursuit of an impossible measurement? 3 astronomers, 3 telescopes, 3 different stars became the focus of the most important astronomical race in human history during the late 1830s, when technological advances finally made stellar parallax detection theoretically possible for the first time. Friedrich Wilhelm Bessel in Prussia targeted the faint double star 61 Cygni using a revolutionary heliometer at Königsberg Observatory, convinced that this seemingly insignificant stellar system possessed the large proper motion that might indicate proximity to our solar system. Thomas Henderson in Cape Town, South Africa, directed his observations toward Alpha Centauri during his survey of southern hemisphere stars, recognizing that this bright stellar beacon represented one of the most promising candidates for parallax detection based on its brilliance and distinctive characteristics. Friedrich Struve in Estonia focused his efforts on bright Vega using the finest refracting telescope available at Dorpat Observatory, believing that this prominent northern star offered the best combination of brightness and observational accessibility for precision positional measurements. The winner would unlock the first distance measurement to another star beyond our Sun, establishing the fundamental scale of the universe and resolving the ancient debate about cosmic dimensions that had puzzled humanity since antiquity. The cosmic distance scale hung in the balance as these 3 competitors employed different strategies, instruments, and observational techniques in their parallel quests to achieve what many considered impossible. Bessel's methodical approach relied on the superior design of his Fraunhofer heliometer, a specialized instrument featuring a split objective lens that could create 2 overlapping images of stellar fields, allowing precise measurement of relative angular positions between nearby stars and more distant reference points. This German astronomer possessed unmatched expertise in positional astronomy and had spent decades refining observational techniques for detecting minute angular displacements, making him the most technically qualified participant in this unprecedented competition. Henderson's campaign benefited from his location in the southern hemisphere, which provided optimal viewing conditions for Alpha Centauri throughout the year, while avoiding the atmospheric complications that affected northern hemisphere observations of this important stellar system. His position as director of the Royal Observatory at the Cape of Good Hope offered access to high-quality instruments and ideal observing conditions, though he lacked the specialised equipment advantages enjoyed by his European competitors. Struve commanded the largest and most powerful refracting telescope in the world at that time, the Dorpat 9-inch refractor manufactured by Joseph von Fraunhofer, which provided exceptional optical quality and light-gathering capability for observing relatively faint reference stars near Bright Vega. This Estonian astronomer had established himself as one of Europe's leading double-star observers and possessed extensive experience with precision measurements of stellar positions and orbital motions. Each participant faced unique challenges related to their chosen target stars and observational circumstances. Bessel's selection of 61 Cygni proved strategically brilliant because this binary system exhibited the largest known proper motion of any star visible from northern latitudes, suggesting proximity that might produce detectable parallax effects. However, the system's faintness required long exposure times and careful attention to reference star positions throughout the observational campaign. Henderson's focus on Alpha Centauri offered the advantage of exceptional brightness and suspected proximity based on its prominence in southern skies, but the star's position near the southern celestial pole created complications for precise positional measurements as Earth rotated. Struve's choice of Vega provided excellent brightness and accessibility from his latitude, though the star's rapid rotation and complex spectrum complicated precise position determination. The competition intensified as news of each astronomer's progress filtered through the international scientific community, creating pressure to achieve definitive results before competitors could claim priority. Observational campaigns extended across multiple seasons as each participant accumulated data points needed to establish the sinusoidal variation characteristic of genuine parallax motion. Systematic errors threatened to invalidate months of careful observations, forcing continuous refinement of measurement techniques and instrumental calibrations. Weather conditions, atmospheric turbulence, and seasonal variations in observing circumstances added unpredictable elements to the competition, while instrumental problems and mechanical failures threatened to demand years of dedicated effort. The scientific stakes extended far beyond personal recognition, because confirming stellar parallax would revolutionize astronomy by providing the first direct evidence of Earth's orbital motion while establishing distance measurements that could calibrate the entire cosmic distance ladder. How did an ingenious optical device finally break through the technological barrier that had frustrated astronomers for millennia? Bessel employed a heliometer, a revolutionary telescope featuring an objective lens split precisely in half along its diameter, creating an instrument unlike any previously used for stellar observations and opening new possibilities for unprecedented measurement accuracy. The two halves could slide past each other under precise mechanical control, creating double images of the same stellar field that allowed direct comparison between target stars and reference objects within the same optical system. This innovative design eliminated many sources of systematic error that plagued conventional telescopes because both images originated from the same optical path and suffered identical atmospheric distortions, instrumental aberrations, and environmental influences. The heliometer allowed measurement of tiny angular differences between stars by adjusting the separation of the split lens components until the doubled images of different objects aligned perfectly, enabling astronomers to quantify angular separations with extraordinary precision. Originally developed by Joseph von Fraunhofer for measuring solar diameter variations, the heliometer proved ideally suited for stellar parallax detection because it could measure relative positions between nearby and distant stars without requiring absolute positional references. Night after night through 1837 and 1838, Bessel tracked 61 Cygni's position using this sophisticated instrument, accumulating hundreds of individual measurements while carefully monitoring atmospheric conditions, temperature variations, and instrumental stability. His observational campaign required relentless dedication because stellar parallax detection demanded observations distributed across Earth's entire orbital period to capture the complete sinusoidal variation of apparent stellar position. Bessel's methodical approach involved comparing 61 Cygni's position relative to two faint background stars that appeared motionless due to their enormous distance, using these reference objects as fixed benchmarks for detecting minute changes in his target's apparent location. The binary nature of 61 Cygni actually assisted his measurements because he could track both components simultaneously, providing internal consistency checks and reducing the impact of random observational errors through statistical averaging. Each night's observations required multiple independent measurements of the same stellar configuration to identify and eliminate spurious readings caused by atmospheric turbulence, instrumental flexure, or observer fatigue. Bessel developed rigorous data reduction procedures that accounted for known systematic effects, including atmospheric refraction, proper motion of the target stars, precession of Earth's rotation axis, and mechanical variations in his telescope mounting system. He detected a shift of 0.314 arcseconds, an angular displacement equivalent to the width of human hair viewed from 10 kilometers away, representing the smallest astronomical measurement successfully achieved by 18th or 19th century technology. This extraordinary precision required not only superior instrumentation, but also revolutionary approaches to error analysis and statistical interpretation of observational data. Bessel's success depended critically on his choice of target, because 61 Cygni exhibited the largest proper motion of any star known at that time, suggesting proximity that might produce detectable parallax effects, while providing a natural test of his measurement accuracy. The binary system's high proper motion allowed Bessel to distinguish between systematic instrument errors and genuine stellar displacement, because proper motion effects accumulated linearly over time, while parallax variations followed the sinusoidal pattern of Earth's orbital geometry. Temperature compensation became crucial because seasonal variations affected the mechanical dimensions of his telescope and mounting system, requiring careful calibration to separate thermal effects from genuine astronomical phenomena. Bessel's observational logs reveal meticulous attention to environmental conditions, recording temperature, humidity, atmospheric pressure, and wind patterns that might influence measurement precision throughout his 2-year campaign. The heliometer's unique design provided several advantages over conventional telescopes for parallax detection, including superior mechanical stability, reduced sensitivity to atmospheric turbulence, and the ability to make direct relative measurements without external reference systems. Fraunhofer's optical craftsmanship ensured exceptional image quality across the split objective lens, while precision mechanical systems allowed reproducible adjustments of the lens and separation with tolerances measured in micrometers. Bessel's triumph established the heliometer as the premier instrument for precision astronomical measurements, inspiring construction of similar devices at observatories worldwide, and revolutionizing techniques for stellar position determination, double star measurements, and planetary observations requiring extreme angular precision. What cruel twist of scientific fate prevented the true pioneer of stellar distance measurement from receiving proper recognition for his groundbreaking achievement? Thomas Henderson actually measured Alpha Centauri's parallax first during his systematic observations conducted between 1832 and 1833, while serving as director of the Royal Observatory at the Cape of Good Hope in South Africa. His result yielded 1.16 arcseconds, approximately 50% larger than the true value, but remarkably close considering the primitive instruments and techniques available during that early period of precision astronomy. Henderson's measurement campaign preceded Bessel's famous work by several years, yet scientific history overlooks this crucial fact because the Scottish astronomer lacked confidence in his revolutionary discovery. Fearing his result appeared impossibly large and violated contemporary understanding of cosmic scales, Henderson hesitated to publish his findings despite possessing observational evidence that could have established him as the first person to measure interstellar distance. The scientific community of the early 19th century expected stellar distances to be vast, but not quite as enormous as Henderson's measurements suggested, creating psychological pressure against announcing results that challenged conventional astronomical wisdom. Only after Bessel's triumphant announcement in 1838 did Henderson finally share his findings in 1839, though by then his priority claim had been overshadowed by the German astronomer's well-publicized success. History remembers Bessel as first, though Henderson's courage might have earned that honor if he had trusted his observations and published them immediately upon completing his analysis. This tragic example illustrates how scientific progress sometimes depends not just on technical capability, but also on the psychological willingness to embrace revolutionary discoveries that contradict established expectations. Henderson's observational campaign at Cape Town provided ideal conditions for studying Alpha Centauri, because this southern hemisphere location offered year-round access to the target star without the atmospheric complications that affected northern hemisphere observations. The Royal Observatory possessed high-quality instruments including a transit circle and meridian telescope that enabled precise positional measurements, though these devices lacked the specialised features of Bessel's heliometer. Henderson's methodical approach involved comparing Alpha Centauri's position relative to numerous background reference stars distributed around the stellar field, accumulating positional data across multiple seasons to detect any systematic variations correlated with Earth's orbital motion. His observational technique required enormous patience because each measurement demanded careful alignment of telescope crosshairs with stellar positions while compensating for atmospheric refraction, instrument calibration errors, and the constant motion of celestial objects across the field of view. Henderson recognized that his large parallax value implied Alpha Centauri resided at distances much smaller than most contemporary estimates suggested, placing this prominent star system closer to Earth than anyone had previously imagined possible. The implications of his measurement extended far beyond simple distance determination, because confirming such proximity would revolutionize understanding of stellar luminosities, galactic structure, and the fundamental scale of the universe itself. Henderson's scientific training included extensive experience with precision measurements and error analysis, yet even he struggled to accept results that appeared to challenge the conventional wisdom about cosmic architecture and stellar distances. His hesitation reflected the conservative nature of early 19th century astronomy, where extraordinary claims required extraordinary evidence and premature publication of controversial results could damage professional reputations permanently. The scientific culture of that era emphasized caution over boldness, particularly for measurements that contradicted established theories or suggested revolutionary modifications to accepted cosmological models. Henderson's position as director of a major observatory carried significant responsibilities that may have influenced his decision to delay publication until other astronomers could confirm the reality of detectable stellar parallax. His eventual publication in 1839 provided crucial supporting evidence for Bessel's discovery, while establishing Alpha Centauri as humanity's nearest stellar neighbour beyond the solar system. Modern analysis of Henderson's original observations reveals that his measurement accuracy was remarkable given the limitations of early 19th century instruments and techniques, achieving results within a factor of 2 despite lacking the specialised equipment and refined methods employed by his more famous competitor. Henderson's story demonstrates how scientific breakthroughs often involve multiple independent discoveries, with recognition typically awarded to researchers who possess both technical skill and the confidence to publicise controversial findings immediately upon their completion. The tragedy of Henderson's delayed publication highlights the importance of scientific communication and the role of institutional support in encouraging astronomers to share revolutionary discoveries with the broader research community. How did 2 simple angular measurements shatter every assumption about the size and scale of our universe? Bessel's groundbreaking calculation placed Cassini at 10.4 light-years away, a distance so staggering that contemporary scientists struggled to comprehend its implications for cosmic architecture and the fundamental nature of space itself. Henderson's subsequent analysis revealed Alpha Centauri at 4.37 light-years from Earth, establishing this brilliant southern star as our nearest stellar neighbour, while confirming that even the closest celestial objects beyond our solar system existed at distances that defied human imagination. These revolutionary measurements dwarfed anything previously contemplated by astronomers, natural philosophers, or theologians who had speculated about cosmic dimensions without any empirical foundation for their estimates. Stars were not merely positioned beyond the planetary spheres as ancient models suggested, but rather separated from our world by gulfs millions of times greater than the distances between planets and our central sun. The universe suddenly expanded beyond human comprehension in a single transformative decade that forever altered our understanding of cosmic geography, stellar populations, and the fundamental organization of matter throughout space. Prior to these parallax breakthroughs, even the most liberal estimates of stellar distances fell short of reality by enormous factors that reflected the complete inadequacy of pre-telescopic observational capabilities. Medieval and Renaissance astronomers had proposed that stars might reside at distances hundreds or perhaps thousands of times greater than planetary separations, but none anticipated the true magnitude of interstellar space revealed by precision angular measurements. The light year itself had no meaning before these discoveries because astronomical distances had never been measured with sufficient accuracy to require such enormous units of measurement. Bessel's result implied that light from 61 Cygni required over 10 years to traverse the cosmic void, separating that stellar system from our own, introducing concepts of cosmic time and space that stretched human understanding to its breaking point. Henderson's measurements suggested that our nearest stellar neighbour resided at a distance requiring over 4 years for light to complete its journey, establishing a minimum baseline for cosmic isolation that emphasised our profound separation from other star systems. These findings revealed that the spaces between stars contained essentially nothing but vacuum, creating a universe dominated by emptiness rather than the dense packing of celestial spheres envisioned by classical cosmology. The implications extended far beyond simple distance measurements because stellar parallax confirmed that Earth indeed orbited the Sun, as Copernican theory predicted, providing long-sought observational evidence for heliocentrism after centuries of theoretical debate. The measured distances also revolutionized understanding of stellar luminosities because stars that appeared relatively faint in our sky might actually shine with tremendous intrinsic brightness while residing at enormous distances from our observational vantage point. Conversely, nearby stars of modest luminosity could appear prominent in terrestrial skies despite generating far less energy than distant stellar giants. The distance scale established by parallax measurements provided the first reliable method for calculating absolute stellar magnitudes, separating apparent brightness from intrinsic energy output and enabling meaningful comparisons between different stellar types. These revelations transformed stellar astronomy from a qualitative science focused on cataloguing apparent positions and brightnesses into a quantitative discipline capable of determining physical properties including stellar masses, radii, surface temperatures, and evolutionary states. The new distance measurements also implied that our solar system occupied an essentially random position within a vast galactic structure containing countless other star systems distributed across enormous volumes of space. If typical stellar separations measured several light years, then our galaxy must contain billions of individual stars scattered across dimensions measured in tens of thousands of light years, creating cosmic structures far larger than anyone had previously contemplated. The parallax discoveries initiated a cascade of revelations about galactic structure, stellar evolution, and cosmic history that continues to this day as astronomers probe ever deeper into space and time. John Herschel eloquently captured the transformative nature of these measurements when he described stellar parallax detection as the greatest triumph of practical astronomy, recognizing that these humble angular measurements had fundamentally redefined humanity's place in the cosmos. The universe revealed by parallax astronomy was not the cozy, human-scaled cosmos of classical antiquity, but rather an almost incomprehensibly vast arena where our entire solar system represented merely a tiny speck of matter lost in cosmic immensity. These distance measurements established the foundation for modern astrophysics by providing the spatial framework necessary for understanding stellar physics, galactic dynamics, and cosmological evolution across billions of years of cosmic history. How did humanity overcome the fundamental atmospheric barrier that had limited stellar measurements for centuries until the space age finally arrived? Earth's turbulent atmosphere blurs stellar positions through constantly shifting pockets of air at different temperatures and densities, creating the twinkling effect we observe with naked eyes, while simultaneously limiting ground-based telescopic accuracy to fractions of an arc-second regardless of optical quality or mechanical precision. Atmospheric seeing represents an insurmountable physical barrier because thermal currents, wind patterns, and pressure variations continuously distort incoming starlight, causing apparent stellar positions to dance randomly around their true locations with amplitudes that often exceed the parallax signals astronomers seek to measure. Even the world's largest and most sophisticated ground-based telescopes cannot achieve positional accuracies better than several tenths of an arc-second when observing through Earth's restless atmospheric layers, making precision parallax measurements extremely challenging. Despite centuries of instrumental improvements and observational refinements, the 1989 Hipparcos satellite revolutionized stellar astrometry by escaping atmospheric limitations entirely, achieving precision measurements accurate to thousandths of an arc-second while operating in the pristine vacuum of space beyond Earth's atmospheric interference. This European Space Agency mission represented humanity's first dedicated astrometric satellite, designed specifically for measuring stellar positions, proper motions and parallaxes with unprecedented accuracy across the entire celestial sphere. Hipparchos mapped 100,000 stars with extraordinary precision, providing the first comprehensive catalogue of stellar distances accurate enough to establish reliable foundations for galactic structure studies and stellar physics investigations throughout the solar neighbourhood. The satellite's sophisticated scanning strategy involved continuous rotation while systematically observing target stars through two telescopes separated by a precise angle, enabling simultaneous measurements of stellar positions relative to the mission's internal reference frame. These observations accumulated over nearly 4 years of continuous operation, generating millions of individual measurements that were processed using advanced statistical techniques to extract parallax signals from observational noise and systematic errors. ESA's Gaia mission, launched in 2013, represents a quantum leap forward in astrometric capability by achieving micro-arcsecond precision measurements that surpass Hipparchos accuracy by factors of 100 or more for bright stellar targets. This revolutionary spacecraft operates from the second Lagrange point, positioned 1.5 million kilometers beyond Earth in the anti-solar direction, where gravitational forces from Earth and Sun balance perfectly to maintain a stable observational platform. Gaia's unprecedented precision stems from its advanced optical system featuring 2 telescopes with sophisticated focal plane arrays containing over 1 billion pixels, each capable of detecting minute changes in stellar brightness and position with extraordinary sensitivity. The mission employs continuous scanning observations that sweep across the entire sky repeatedly, building up comprehensive measurements through systematic coverage rather than targeted observations of individual stellar systems. Gaia observes each target star approximately 70 times over its 5-year nominal mission duration, accumulating sufficient data points to extract parallax signals with statistical confidence while identifying and correcting for various systematic effects that could contaminate distance measurements. The spacecraft's thermal design maintains incredible stability by operating at temperatures near absolute zero, eliminating temperature-induced dimensional changes that plagued earlier ground-based instruments with seasonal variations and thermal cycling effects. Advanced onboard processing systems automatically identify stellar sources, measure their positions and brightness, and transmit compressed data to Earth-based receiving stations for detailed analysis using supercomputer facilities dedicated to Gaia data reduction. The mission's ambitious goals include mapping over 1 billion stars throughout our galaxy, extending precise parallax measurements to distances of several thousand light-years and creating the most detailed 3-dimensional map of stellar positions ever attempted by human technology. Gaia's extraordinary precision enables detection of parallax angles smaller than the apparent size of a human hair viewed from the distance between Earth and Moon, pushing measurement capabilities into previously unimaginable realms of cosmic surveying. The satellite's continuous observations also reveal stellar, proper motions with unprecedented accuracy, tracking the actual movement of stars through space as they orbit our galaxy's centre and interact gravitationally with neighbouring stellar systems. These proper motion measurements provide crucial information about galactic rotation, stellar kinematics, and the distribution of dark matter throughout our cosmic neighbourhood, while identifying stellar streams, associations, and other structures invisible to conventional astronomical surveys. What astronomical achievement represents the most ambitious mapping project ever undertaken by human civilization? 1 billion stars measured across our cosmic neighbourhood represents approximately 1% of the entire Milky Way galaxy, creating an unprecedented census that catalogues stellar positions, motions, and distances with extraordinary precision throughout our galactic environment. Gaia's comprehensive survey extends far beyond simple star counting to establish the most detailed 3-dimensional map of stellar architecture ever constructed, revealing intricate patterns of galactic rotation, stellar associations, and cosmic structure invisible to previous observational campaigns. Distances accurate to 0.001% for nearby stars like Alpha Centauri demonstrate the remarkable precision achieved by this revolutionary space mission, providing measurements so exact they approach the fundamental limits imposed by quantum mechanics and relativistic effects on electromagnetic radiation propagating across interstellar space. Each individual measurement requires detecting angular shifts smaller than the width of a virus particle, pushing technological capabilities into realms where atomic-scale mechanical tolerances become critical for mission success, and where thermal fluctuations measured in billionths of degrees can compromise observational accuracy. The satellite operates from its unique vantage point 1.5 million kilometers from Earth, positioned beyond the Moon at the second Lagrange point where gravitational forces maintain perfect orbital stability without requiring constant propulsive corrections that might disturb its delicate measurement systems. This remote location provides optimal observing conditions free from Earth's gravitational perturbations, atmospheric interference, and electromagnetic contamination, while maintaining continuous communication links with ground-based mission control facilities. Gaia's scanning strategy involves perpetual rotation at a carefully controlled rate that sweeps both telescopes across the entire celestial sphere every 6 hours, ensuring systematic coverage of all accessible stellar targets while building up statistical precision through repeated observations distributed across the mission timeline. The spacecraft's focal plane contains 106 charge-coupled device detectors arranged in precise geometric patterns that capture stellar images with sub-pixel accuracy, enabling measurement of stellar positions to precisions measured in arc-seconds through sophisticated image processing algorithms. Advanced onboard computers automatically identify stellar sources within each detector field, measure their precise positions and brightnesses, and compress this information for transmission to Earth using efficient data encoding schemes that maximize scientific return within available communication bandwidth limitations. Ground-based data processing centers employ massive computational resources to analyze incoming observations, applying complex, mathematical models that account for relativistic effects, instrumental calibrations, and systematic errors, while extracting genuine parallax signals from accumulated measurements spanning multiple years. The mission's extraordinary sensitivity enables detection of stellar parallax angles equivalent to observing a European coin from the surface of the Moon, demonstrating humanity's remarkable ability to measure cosmic distances using nothing more than precise angular determinations and fundamental geometric principles. Gaia's comprehensive stellar census includes not only main sequence stars like our Sun, but also exotic objects including white dwarfs, red giants, binary systems, variable stars, and even extrasolar planets detectable through their gravitational influence on host star positions. The satellite's continuous monitoring reveals stellar proper motions with unprecedented accuracy, tracking actual movement of individual stars through space as they complete their orbital journeys around our galaxy's central supermassive black hole over timescales measured in hundreds of millions of years. These kinematic measurements provide crucial insights into galactic dynamics, dark matter distribution, and stellar formation histories, while identifying previously unknown stellar streams created by tidal disruption of ancient globular clusters and dwarf galaxies. Gaia's parallax measurements extend reliable distance determinations throughout the solar neighbourhood and into the galactic disk, providing fundamental calibration standards for other distance measurement techniques used to probe more remote cosmic structures. The mission's impact on astrophysics extends far beyond simple distance measurements because accurate stellar parallaxes enable precise determination of intrinsic stellar luminosities, masses, ages, and evolutionary states through comparison with theoretical stellar evolution models. Revolutionary discoveries emerging from Gaia data include identification of stellar populations with distinct kinematic signatures, detection of gravitational waves through their effects on stellar positions, and measurement of general relativistic light bending around massive stellar objects throughout our galactic vicinity. How precisely can modern astronomy measure the distance to our nearest stellar neighbour, using techniques that would astound the pioneers who first detected stellar parallax? Modern measurements give Alpha Centauri A and B a distance of 4.344 light-years away, representing the culmination of nearly 2 centuries of technological advancement and observational refinement since Henderson and Bessel first attempted to quantify interstellar distances using primitive 19th century instruments. Proxima Centauri sits at 4.2465 light-years from our solar system, establishing this faint red dwarf as our absolute closest stellar neighbour and the primary target for any future interstellar exploration missions that humanity might eventually undertake. The parallax measurement for Proxima Centauri yields 0.7685 plus or minus 0.0002 arcs-seconds, demonstrating precision that surpasses Henderson's original estimates by factors of thousands while achieving uncertainty levels smaller than the systematic errors that plagued even the finest ground-based observations throughout the 20th century. This extraordinary precision represents the angular width of a quarter coin observed from 4,000 kilometers away, an analogy that illustrates humanity's remarkable ability to detect and quantify cosmic motions occurring on scales that dwarf terrestrial measurement capabilities. The current distance determination is so exact that astronomers know Alpha Centauri's location to within 3 billion kilometers, an uncertainty that sounds enormous by human standards but represents less than 20 astronomical units, or roughly twice the distance between our Sun and Uranus. Such precision enables detailed studies of the Alpha Centauri system's orbital dynamics, gravitational interactions, and potential planetary companions that would be impossible without accurate knowledge of the fundamental distance scale governing this stellar trio. Advanced space-based astrometry missions like Gaia achieved these remarkable precisions through continuous observations spanning multiple years, accumulating thousands of individual measurements that are processed using sophisticated statistical algorithms designed to extract genuine parallax signals from instrumental noise and systematic effects. The measurement uncertainty of 0.0002 arc-seconds corresponds to angular precision roughly 10,000 times better than the human eye can resolve under ideal conditions, requiring technological capabilities that push against fundamental physical limitations imposed by photon statistics and quantum mechanical uncertainties. Temperature stability becomes critical for such precise measurements because thermal expansion of spacecraft structures by even nanometers can introduce systematic errors that masquerade as genuine parallax effects, demanding unprecedented engineering tolerances in space-based observational platforms. Gravitational perturbations from planets, asteroids, and interstellar matter can influence spacecraft trajectories and orientation with sufficient magnitude to compromise microarc-second level measurements, requiring continuous monitoring and correction of observational geometry throughout multi-year mission operations. The Alpha Centauri distance measurements also provide crucial calibration standards for testing general relativistic effects on electromagnetic radiation propagating through curved spacetime near massive objects, enabling precision tests of Einstein's theoretical predictions using astronomical observations rather than laboratory experiments. These measurements reveal that light from Alpha Centauri experiences gravitational redshift effects as photons climb out of the stellar gravitational wells before beginning their 4-year journey across interstellar space to reach terrestrial detectors. Modern parallax determinations also account for the proper motion of Alpha Centauri through space relative to our solar system, separating genuine parallax effects from the linear displacement caused by the star's actual movement through our galactic neighbourhood over observational timescales. The combined Alpha Centauri system exhibits proper motion of approximately 3.7 arc-seconds per year, representing actual velocity through space of roughly 22 kilometers per second relative to our solar reference frame. This substantial proper motion initially complicated parallax measurements because the linear displacement accumulated over yearly observation periods could exceed genuine parallax effects unless carefully separated through detailed kinematic analysis. Contemporary distance measurements incorporate corrections for relativistic effects, including stellar aberration caused by Earth's orbital motion, gravitational light deflection near the Sun during certain observation geometries, and time dilation effects that influence the apparent timing of electromagnetic signals propagating across vast interstellar distances. What fundamental truth about the nature of time and space becomes clear when we grasp the meaning behind the cosmic speed limit that governs our universe? Light travels at exactly 299,792,458 meters per second through the vacuum of space, representing the absolute speed limit that constrains all electromagnetic radiation and information transfer throughout the cosmos. This velocity appears inconceivably fast by human standards, yet it becomes almost painfully slow when applied to the vast scales separating stellar systems across our galactic neighbourhood. In 1 year, light covers 9.461 trillion kilometers as it races through the emptiness between stars, a distance so enormous that even this fundamental constant of physics requires substantial time to bridge the cosmic gulfs that isolate stellar systems from one another. At this unimaginable speed that allows light to circle Earth 7.5 times in a single second, electromagnetic radiation from Alpha Centauri still requires 4.37 years to complete its journey across interstellar space and reach our terrestrial detectors. The starlight entering your eyes tonight actually departed its stellar source when global events were dramatically different from current circumstances, carrying information about conditions that existed in the Alpha Centauri system during a previous epoch of human history. You are seeing Alpha Centauri not as it exists at this moment, but rather as it appeared years ago when that particular batch of photons began their long voyage through the cosmic void separating our solar systems. This fundamental delay between stellar events and our observation of them transforms astronomy into a form of time travel where every telescopic observation reveals the universe's past rather than its present state. The concept of simultaneity loses meaning across interstellar distances because events occurring right now in the Alpha Centauri system will remain invisible to Earth-based observers until those photons complete their multi-year journey through space. If Alpha Centauri were to suddenly cease nuclear fusion and extinguish itself tonight, human civilization would continue observing its normal stellar output for over 4 additional years before detecting this catastrophic event. Conversely, any dramatic changes in our solar system would remain undetectable to hypothetical observers in the Alpha Centauri system until light carrying that information traversed the same 4-year communication delay. This temporal disconnect emphasizes how stellar astronomy operates fundamentally differently from terrestrial observations where light travel delays remain negligible for practical purposes. The finite speed of light creates cosmic horizons beyond which information cannot propagate, establishing fundamental limits on causality and communication throughout the universe. Even if advanced civilizations existed in the Alpha Centauri system and possessed technology for interstellar communication, meaningful conversations would require nearly 9 years for simple question and answer exchanges due to signal propagation delays. The light year emerges as a natural unit for measuring cosmic distances precisely because it represents the fundamental relationship between space and time that governs the electromagnetic phenomena throughout our universe. 1 light year equals approximately 9.5 trillion kilometers, a distance that dwarfs human transportation capabilities while providing convenient scaling for astronomical distance measurements. The Alpha Centauri system's position at 4.37 light-years establishes the minimum baseline for interstellar exploration, representing the closest possible destination for any hypothetical spacecraft attempting to leave our solar system and visit another star. This distance implies that even theoretical spacecraft traveling at significant fractions of light speed would require years or decades to complete interstellar journeys, making such voyages multi-generational endeavours that exceed typical human lifespans. The reality of light speed limitations means that interstellar exploration necessarily involves either extremely long journey times, revolutionary propulsion technologies, or acceptance of one-way missions where travellers cannot expect to return to their original homes. These constraints explain why interstellar travel remains purely theoretical despite humanity's remarkable achievements in planetary exploration and space technology development throughout the past century. How does the human concept of time crumble when confronted with the true scale of interstellar distances that separate our world from its nearest stellar neighbours? If you could somehow drive to Alpha Centauri at highway speed averaging 100 km per hour without stopping for fuel, food or rest, this impossible journey would require 48 million years to complete, a time span that encompasses the entire evolutionary progression from early mammals to modern humans hundreds of times over. This staggering duration extends across geological epochs that witnessed the rise and extinction of countless species, the formation and erosion of mountain ranges, the advance and retreat of ice ages, and dramatic shifts in continental positions due to plate tectonic processes. Voyager 1, humanity's fastest and most distant spacecraft currently racing through interstellar space at 17 kilometers per second, would still need 73,000 years to reach Alpha Centauri if it were aimed in the correct direction, rather than heading toward the constellation of Fucus. This duration exceeds the entire span of recorded human history by factors of 10 or more, encompassing periods longer than the development of agriculture, the rise of civilizations, the invention of writing, and all technological progress achieved since the last ice age ended. A single human lifetime represents barely a cosmic heartbeat against such immense distances, lasting perhaps 80 years compared to interstellar journey times, measured in tens of thousands of years or more depending on propulsion technology. Even the longest-lived human institutions, including religions, empires, and cultural traditions, rarely persist for more than a few millennia before evolving beyond recognition or disappearing entirely from historical records. The time required for interstellar travel using current technology exceeds the stability period of human languages, political systems, and technological paradigms, making it virtually impossible to plan coherent interstellar missions using contemporary organizational structures or scientific knowledge. Generational spacecraft would need to maintain technical capability and mission focus across hundreds or thousands of generations, requiring social and technological stability far beyond anything achieved in human experience. The psychological challenges facing interstellar travelers would include not only the physical hardships of space travel, but also the knowledge that their departure represents permanent separation from Earth and everyone they leave behind. Even light, the fastest phenomenon known to physics and the universal speed limit that constrains all information transfer throughout the cosmos, crawls across this void at what becomes an agonizingly slow pace when measured against human impatience and mortality. The 4-year communication delay between Earth and Alpha Centauri means that interstellar conversations would require nearly a decade for simple exchanges, making real-time coordination impossible for any joint ventures between stellar systems. Radio signals carrying news, scientific discoveries, or personal messages would arrive years after transmission, creating temporal disconnections that challenge conventional concepts of community and shared experience. The relativistic effects predicted by Einstein's theories offer some hope for reducing subjective travel times at very high velocities, but achieving such speeds would require energy expenditures and technological capabilities far beyond current human achievements. At 90% of light speed, time dilation would reduce the subjective journey's time to approximately 2 years for travelers, while over 4 years elapsed on Earth. But reaching such velocities demands revolutionary advances in propulsion physics and engineering. The energy requirements for accelerating even modest payloads to relativistic speeds approach the total energy output of major industrial nations, highlighting the enormous technological barriers facing practical interstellar exploration. These temporal constraints explain why serious discussions of interstellar travel often focus on robotic probes rather than human crews, accepting that exploration missions must be designed as one-way voyages, with no expectation of direct benefits for the launching civilization. The vast timescales involved in interstellar exploration force humanity to think beyond immediate gratification and consider projects spanning multiple generations, requiring unprecedented coordination between current and future societies that may have radically different values, technologies, and priorities. What fundamental laws of physics conspire to make interstellar travel not just difficult, but theoretically impossible, using conventional approaches to spacecraft propulsion? According to Einstein's special theory of relativity, nothing possessing mass can reach light speed because the energy requirements grow without bound as velocity approaches this cosmic speed limit, creating an insurmountable barrier that governs all the matter and energy interactions throughout the universe. As objects approach light speed, their relativistic mass effectively becomes infinite, while their length contracts towards zero in the direction of motion, requiring infinite energy inputs to achieve the final increment of velocity that would equal electromagnetic radiation speed. The energy required to accelerate matter to light speed becomes impossible to achieve using any conceivable power source, because the mass-energy relationship described by Einstein's famous equation demonstrates that kinetic energy approaches infinity as velocity nears the speed of light. Even reaching 99.9% of light speed would demand energy expenditures equivalent to the total output of multiple stars over extended periods, far exceeding the energy production capabilities of entire galactic civilizations. The universe sets fundamental limits on how quickly we can cross these cosmic gulfs through physical laws that operate independently of human desires or technological ambitions, constraining all transportation methods to velocities well below the theoretical maximum allowed by relativistic physics. These constraints emerge from the basic structure of space-time itself, rather than mere technological limitations that might be overcome through engineering advances or scientific breakthroughs. Even at the seemingly impressive velocity of 99.9% of light speed, the journey to Alpha Centauri would still require over 4 years of subjective travel time for hypothetical passengers, while significantly longer periods elapsed on Earth due to relativistic time dilation effects. The relativistic momentum of objects increases dramatically as their velocity approaches light speed, requiring exponentially greater force applications to achieve each additional increment of acceleration beyond 90% of the cosmic speed limit. Practical spacecraft designs must account for the enormous energy costs associated with relativistic travel, while recognizing that diminishing returns make extreme velocities economically and physically unfeasible regardless of available technology. The energy required to accelerate a modest spacecraft to half the speed of light equals the explosive energy of hundreds of nuclear weapons, demonstrating the enormous power requirements involved in even modest attempts at relativistic propulsion. Antimatter propulsion systems, often proposed as theoretical solutions for interstellar travel, would need to carry antimatter fuel masses comparable to the spacecraft payload itself, creating additional challenges related to containment, storage, and safety during extended voyages. The fundamental physics of rocket propulsion imposes logarithmic relationships between fuel mass and achievable velocity that become prohibitively demanding for relativistic spacecraft attempting to carry both passengers and sufficient fuel for deceleration at their destination. Alternative propulsion concepts, including fusion rockets, ion drives, and solar sails, offer improved efficiency compared to chemical rockets but remain constrained by the same relativistic limitations that prevent any material object from reaching light speed. Breakthrough propulsion concepts such as Alcubierre drives or wormhole transportation require exotic matter with negative energy densities that may not exist in nature and would demand manipulation of space-time geometry using technologies far beyond current human understanding. The laws of thermodynamics impose additional constraints on interstellar propulsion systems because perfect energy conversion efficiency remains impossible, and waste heat. Generation becomes problematic for high-power spacecraft operating in the vacuum of space where radiative cooling provides the only mechanism for thermal management. Quantum mechanical effects become significant at relativistic velocities where particle interactions with the interstellar medium generate high-energy radiation that would sterilize any biological passengers, while potentially damaging electronic systems and structural materials throughout extended journeys. What radical departure from traditional spacecraft design could potentially overcome the seemingly impossible barriers to interstellar exploration within human lifetimes? Ultra-light spacecraft weighing just grams rather than tons represent a revolutionary approach that abandons conventional notions of crewed exploration in favor of miniaturized robotic probes capable of achieving velocities impossible for massive vehicles carrying human passengers and life support systems. These microscopic explorers would sacrifice payload capacity and mission complexity in exchange for the ability to reach unprecedented speeds using propulsion methods that become feasible only when spacecraft mass drops to negligible levels. Powered by 100 billion watts of laser light concentrated from Earth-based arrays, these diminutive craft would harness photon momentum to achieve acceleration rates thousands of times greater than any chemical rocket, while avoiding the tyranny of carrying propellant that increases exponentially with desired velocity. The laser propulsion concept exploits the fundamental physics of electromagnetic radiation pressure, where photons carry momentum that can be transferred to reflective surfaces through purely optical interactions that require no onboard fuel or reaction mass. Accelerated to 20% of light speed in just 10 minutes, these ultralight probes would experience acceleration forces measured in millions of Earth gravities, far beyond the tolerance of any biological organism, but potentially survivable for appropriately designed electronic systems and structural materials. The brief acceleration phase would occur entirely within our solar system using ground-based laser arrays positioned across multiple continents to maintain continuous illumination as Earth rotates and the spacecraft rapidly gains distance from its launch point. Journey time to Alpha Centauri would shrink to 20 to 25 years using this approach, representing the first realistic proposal for interstellar exploration that could deliver results within single human lifetimes rather than requiring multi-generational commitment from launching civilizations. These miniature spacecraft would zip through the Alpha Centauri system in mere days, never slowing down due to the impossibility of carrying deceleration systems or the impracticality of building laser arrays at the destination to reverse the acceleration process. The fly-by nature of such missions demands sophisticated, onboard systems capable of rapid data collection, processing and transmission during the brief encounter window when scientific targets remain within instrument range. Advanced miniaturization technologies would compress cameras, spectrometers, magnetometers, and communication systems into packages weighing mere grams while maintaining sufficient capability to gather meaningful scientific data about stellar properties, planetary systems, and interstellar medium composition. The laser array required for this ambitious project would consist of millions of individual laser units distributed across Earth's surface to generate the enormous power levels needed for spacecraft acceleration, while providing redundancy against equipment failures and atmospheric interference. Atmospheric turbulence poses significant challenges for ground-based laser propulsion, because distortions that scatter or defocus the laser beam reduce propulsion efficiency and could destroy delicate spacecraft components through uneven heating or optical damage. Breakthrough Starshot researchers propose adaptive optic systems similar to those used in modern astronomical telescopes to compensate for atmospheric effects in real time, maintaining precise laser focus on rapidly receding spacecraft over distances spanning millions of kilometers. The technological challenges include developing ultra-lightweight materials capable of surviving intense laser illumination, designing communication systems powerful enough to transmit data across interstellar distances using minimal power sources, and creating autonomous navigation systems that can operate reliably for decades without ground-based control or maintenance. Spacecraft design must balance competing requirements for minimal mass, structural integrity, thermal management, radiation shielding, and scientific instrumentation within severe constraints imposed by the laser propulsion acceleration profile and interstellar environment hazards. The project represents humanity's first serious attempt to engineer practical solutions for interstellar exploration, rather than relying on theoretical propulsion concepts that remain far beyond current technological capabilities. How would the fundamental challenges of interstellar communication compound the already daunting obstacles facing humanity's first robotic ambassadors to another star system? At 20% of light speed, relativistic effects would distort the spacecraft's perspective of space and time in subtle but measurable ways that could affect instrument calibrations, clock synchronization, and data processing algorithms throughout the multi-decade journey to Alpha Centauri. The Doppler shift would dramatically alter the apparent frequency of electromagnetic radiation encountered during the voyage, requiring sophisticated onboard processing to compensate for these relativistic distortions when analyzing scientific measurements of the interstellar medium and destination stellar system. Radio signals from the craft would require 4.37 years to traverse the interstellar void and reach Earth-based receiving stations, creating an enormous communication delay that eliminates any possibility of real-time mission control or adaptive responses to unexpected discoveries during the flyby encounter. By the time we receive the first images and scientific data from the Alpha Centauri system, the probe would be long gone, racing deeper into interstellar space beyond any hope of course corrections or follow-up observations based on initial findings. The data transmission window might last perhaps minutes as the craft races through the stellar system at 60,000 kilometers per second, demanding that all critical observations occur during this brief encounter while the spacecraft simultaneously attempts to transmit accumulated data back toward Earth. We must build autonomous systems that function flawlessly for decades without repair, maintenance, or external intervention while operating in the harsh radiation environment of interstellar space, where cosmic rays and high-energy particles gradually degrade electronic components. The communication challenge extends beyond simple signal propagation delays to include fundamental questions about data storage, processing priorities, and transmission protocols that must be programmed decades in advance without knowledge of what discoveries might await at the destination. Spacecraft designers must anticipate which scientific measurements will prove most valuable and allocate limited communication bandwidth accordingly, recognizing that transmission opportunities during the flyby encounter will be severely constrained by power limitations and antenna pointing requirements. The inverse square law governing electromagnetic radiation means that signal strength decreases dramatically with distance, requiring either enormous transmitter power or highly sensitive Earth-based receiving systems to detect weak signals arriving from interstellar distances. Advanced error correction algorithms become essential for reconstructing scientific data from corrupted transmissions where individual bits may be lost or altered during the 4-year journey through space filled with the electromagnetic interference and particle radiation. The spacecraft must prioritize data transmission during the brief flyby window, while simultaneously conducting observations, maintaining attitude control, and managing thermal loads from intense stellar radiation encountered at close range to the Alpha Centauri system. Onboard artificial intelligence systems would need unprecedented autonomy to make real-time decisions about scientific priorities, instrument operations, and communication protocols without any possibility of ground-based guidance during critical mission phases. The probe must carry sufficient computational resources to process raw sensor data into compressed formats suitable for interstellar transmission, while maintaining backup systems capable of recovering from radiation-induced failures or software glitches that could cripple the mission. Deep space communication networks on Earth would require significant upgrades to track and communicate with spacecraft traveling at relativistic velocities across interstellar distances, potentially necessitating new antenna designs and signal processing techniques optimized for these extreme operating conditions. The communication protocols must account for the gradual drift of spacecraft trajectory relative to Earth as both objects move through their respective orbital motions around the galactic center during the decades-long mission timeline. What monumental engineering feats would be required to harness the most powerful energy sources known to physics for propelling spacecraft across interstellar distances? Project Orion proposed nuclear explosions to push massive spacecraft using the tremendous energy release from atomics. Weapons detonated behind protective pusher plates, creating impulses powerful enough to accelerate multi-thousand-ton vehicles to velocities impossible with any chemical propulsion system. This audacious concept envisioned spacecraft riding controlled nuclear blasts like cosmic surfboards, absorbing momentum from each explosion through shock absorbers and structural systems designed to survive repeated exposure to temperatures and pressures exceeding those found in stellar cores. At 3 to 5% of light speed, such nuclear pulse spacecraft would still require 100 years or more to complete journeys to Alpha Centauri, representing significant improvements over conventional rockets, while still demanding multi-generational missions exceeding typical human institutional stability. The engineering challenges associated with nuclear pulse propulsion include developing materials capable of withstanding repeated nuclear detonations, creating reliable mechanisms for ejecting and detonating atomic charges at precise intervals, and designing life support systems that protect human crews from radiation exposure throughout extended acceleration phases. Fusion ramjets represent another theoretical approach that could potentially reach 10 to 15% of light speed by collecting interstellar hydrogen using enormous magnetic scoops and compressing this fuel to fusion temperatures within onboard reaction chambers. These hypothetical engines would eliminate the need for carrying propellant by harvesting fuel from the interstellar medium itself, though the engineering requirements include magnetic field generation systems spanning thousands of kilometers and fusion reactors operating under conditions far more extreme than any terrestrial power plant. Each propulsion concept requires technologies we have not yet mastered, despite decades of research into controlled nuclear fusion, magnetic confinement systems, and materials science applications for extreme environments. The engineering challenges grow exponentially with desired speed because relativistic effects compound the difficulties of structural design, thermal management, and radiation shielding as spacecraft velocities approach significant fractions of light speed. Nuclear pulse propulsion demands precise timing mechanisms that coordinate explosive detonations with spacecraft dynamics while maintaining structural integrity under acceleration loads that would crush conventional vehicles like empty beverage cans. Advanced material science must develop structural components and shock absorption systems capable of surviving thousands of nuclear explosions without fatigue failures or degradation that could compromise mission safety during interstellar voyages lasting decades or centuries. Fusion ramjet technology requires breakthroughs in plasma physics, magnetic field control, and high-temperature materials that currently exist only in theoretical models rather than practical engineering applications. The interstellar medium contains insufficient hydrogen density in most regions of space to sustain fusion ramjet operations, potentially limiting such systems to specific galactic environments or requiring hybrid propulsion approaches that combine multiple acceleration methods. Political and safety considerations surrounding nuclear propulsion systems create additional obstacles because launching nuclear-powered spacecraft from Earth raises concerns about accident scenarios that could contaminate terrestrial environments with radioactive materials. International treaties governing nuclear weapons proliferation complicate development of nuclear pulse propulsion because the explosive devices required for spacecraft acceleration share technologies with military applications that are strictly controlled by existing arms limitation agreements. The enormous costs associated with developing revolutionary propulsion systems exceed the resources of individual nations, requiring unprecedented international cooperation and sustained financial commitment over timeframes that challenge typical political and economic planning horizons. Alternative approaches, including antimatter propulsion, offer theoretical advantages in terms of energy density and specific impulse, but demand even more exotic technologies for antimatter production, storage, and controlled annihilation that remain firmly in the realm of science fiction rather than engineering possibility. How does our cosmic neighbourhood reveal humanity's profound isolation within a universe that seems almost designed to keep civilizations separated by impossible distances? Alpha Centauri represents the absolute closest we can approach to another star system, serving as our nearest stellar neighbour in a galactic architecture that places even the most accessible destinations far beyond practical reach using current or foreseeable transportation technologies. Yet this supposed closeness remains almost impossibly remote by any human measure of distance or travel time, requiring spacecraft velocities approaching significant fractions of light speed to complete journeys within single human lifetimes. The nearest 100 stars are scattered across a sphere 20 light-years in radius, centered on our solar system, creating a sparse distribution that emphasizes the vast emptiness characterizing our local galactic environment. Our Sun sits in a relatively sparse region of the Milky Way galaxy known as the local bubble, a cavity carved out by the ancient supernova explosions that swept away much of the interstellar gas and dust, while leaving behind lower stellar densities than found in more typical galactic regions. We exist as islanders on a cosmic ocean with the nearest shore barely visible even through our most powerful telescopes, isolated not by water, but by vacuum so complete it approaches the theoretical limits of emptiness. This isolation extends beyond simple physical separation, because the energy requirements for interstellar travel exceed the total power output of contemporary human civilization by enormous factors, making even robotic exploration of nearby stellar systems extraordinarily challenging endeavours. The local group of stars surrounding our solar system contains fascinating targets, including red dwarf systems that could harbour potentially habitable planets, binary configurations that demonstrate exotic gravitational dynamics, and stellar remnants that reveal the evolutionary endpoints awaiting stars like our Sun. Barnard's star, located 6 light-years distant, approaches our solar system at such high velocity that it will become our closest stellar neighbour within approximately 10,000 years, though even this relatively rapid stellar motion occurs at speeds measured in dozens of kilometres per second, rather than the thousands of kilometres per second required for practical interstellar travel. Wolf 359, another nearby red dwarf system, lies at 7.9 light-years distance while exhibiting fascinating properties including powerful stellar flares that could sterilize any planetary atmospheres within its habitable zone. The Alpha Centauri system itself contains multiple components that offer diverse scientific opportunities, including potential Earth-like worlds orbiting within the habitable zones of the primary stars and confirmed planets around Proxima Centauri that represent the closest known exoplanets to our home world. Stellar surveys reveal that our solar neighbourhood contains an unusual deficit of giant stars and massive stellar systems compared to galactic averages, possibly explaining why Earth has remained relatively free from catastrophic radiation events that could disrupt biological evolution over geological timescales. The three-dimensional distribution of nearby stars shows no obvious clustering or organisation beyond the general tendency for stars to follow similar orbital paths around the galactic centre, suggesting that our cosmic environment lacks the dense stellar associations found in globular clusters or star-forming regions. Interstellar distances in our neighbourhood typically range from several light-years to dozens of light-years, creating separations that would challenge even theoretical spacecraft capable of reaching 10% of light speed, with journey times spanning decades or centuries. The void between stars contains tenuous clouds of hydrogen gas and cosmic dust that create additional hazards for high-speed interstellar spacecraft, while providing scientific opportunities for studying the composition and structure of the interstellar medium through which our solar system travels. Our position within the galactic disk places us approximately 26,000 light-years from the Milky Way's central, supermassive black hole, while positioning us roughly halfway between the galactic centre and the outer edge of the stellar disk. This location provides optimal conditions for stable planetary orbits and biological evolution because we avoid both the intense radiation environment near the galactic core and the metal-poor conditions found in the galaxy's outer regions where heavy elements necessary for rocky planet formation remain scarce. The cosmic perspective reveals that even our closest stellar neighbours exist in fundamental isolation, separated by distances so vast that meaningful communication or travel between stellar systems demands technological capabilities far beyond anything achieved by human civilization, despite centuries of scientific and engineering progress. Could the vast distances separating star systems provide the ultimate explanation for why our searches for extraterrestrial intelligence have yielded only cosmic silence despite billions of years of galactic evolution? If simple life exists elsewhere throughout our galaxy, these enormous interstellar distances may explain our profound cosmic loneliness by creating insurmountable barriers to communication and travel that isolate every biological civilization within its home stellar system. Regardless of technological sophistication or scientific achievement, interstellar exploration requires not just advanced technology, but sustained civilizational commitment spanning timescales that exceed the stability of human institutions, languages, political systems, and even biological species as they evolve and adapt over geological timeframes. The energy costs associated with crossing even the relatively modest distance to Alpha Centauri dwarf current human capabilities by factors of millions or billions, demanding power sources equivalent to the total output of stars rather than the modest energy budgets available to planetary civilizations. Perhaps every alien civilization that has ever emerged throughout cosmic history faces these same impossible distances that transform interstellar travel from an engineering challenge into a fundamental, physical limitation imposed by the structure of space-time itself. The universe appears designed to maintain profound isolation between its living worlds, preventing direct contact between biological intelligences while allowing only the most limited forms of electromagnetic communication across the vast gulfs separating stellar systems. Even civilizations millions of years more advanced than humanity might find interstellar colonization economically and energetically prohibitive when weighed against the resources required for such ambitious projects, compared to the potential benefits of exploring and developing their home stellar systems. The Fermi paradox dissolves when we recognize that interstellar travel demands not merely superior technology, but fundamentally different approaches to energy generation, propulsion physics, and social organization that may be impossible for biological organisms constrained by evolutionary limitations and finite lifespans. Advanced extraterrestrial. Civilizations might choose to focus their efforts on computational simulations, artificial intelligence development, and virtual reality environments rather than attempting to physically traverse the cosmic distances separating their worlds from other stellar systems. The light-speed communication delay between even nearby star systems eliminates the possibility of meaningful real-time interactions, reducing interstellar communication to the exchange of recorded messages that arrive years or decades after transmission, while carrying information about civilizations that may have evolved significantly since the original broadcast. Technological civilizations face diminishing returns when investing in interstellar exploration, because the enormous resource commitments required for such projects could alternatively support countless other scientific endeavours within their home systems, including space habitats, terraforming projects, and computational research that provide immediate benefits to their populations. The psychological barriers facing interstellar exploration may prove even more challenging than the physical obstacles because conscious beings evolved for terrestrial environments might find the isolation and temporal scales associated with interstellar voyages fundamentally incompatible with biological and social needs. Even if advanced propulsion technologies could reduce interstellar journey times to decades or centuries, the social and economic disruptions caused by such expeditions might exceed the capabilities of stable civilizations to organize and sustain over extended periods. The observable universe contains billions of galaxies with trillions of stellar systems that could potentially harbor life. Yet the distances separating these cosmic islands create isolation so complete that meaningful contact between galactic civilizations becomes essentially impossible, regardless of technological advancement. Within individual galaxies, stellar densities in regions like globular clusters might permit easier interstellar travel, but these environments also subject planetary systems to gravitational disruptions and radiation levels that could prevent the emergence or survival of complex biological life over evolutionary timescales. The cosmic perspective suggests that intelligence and consciousness represent rare and precious phenomena that emerge briefly within isolated stellar systems before disappearing again into the cosmic silence that characterizes most of spacetime throughout the universe's history. Our cosmic loneliness may therefore represent not a failure of imagination or technology, but rather the natural consequence of physical laws that govern energy, matter, and information transfer across the enormous scales characterizing our universe. How does Einstein's most counterintuitive prediction offer the only realistic hope for human beings to personally witness the wonders of another star system within their natural lifespans? For travellers at relativistic speeds approaching the cosmic velocity limit, the journey to Alpha Centauri contracts dramatically due to time dilation effects that fundamentally alter the relationship between space and time as experienced by high-velocity observers moving through the universe. At 90% of light speed, astronauts would experience only 2.1 years of subjective time during their interstellar voyage, while Earth-bound observers measure 4.9 years passing according to their reference frame, creating a temporal disconnect that separates the travellers from their home world in ways that extend far beyond simple physical distance. At 99.9% of light speed, hypothetical crew members would age just months during the entire interstellar voyage as their biological processes slow relative to external time. Arriving at Alpha Centauri having experienced only a brief journey, while decades passed in their departure, civilization. But for the loved ones left behind on Earth, the full 4 years and more crawl by at normal temporal rates, creating irreversible separations between interstellar explorers and their families, friends, colleagues, and entire cultural contexts that define human social existence. Relativistic travel becomes possible in principle through time dilation effects, but it represents essentially a one-way ticket through time that transforms interstellar exploration into a form of temporal exile, where travellers can never truly return to the world they originally departed. The psychological implications of relativistic interstellar travel extend far beyond the technical challenges of spacecraft design and propulsion physics, because crew members must accept permanent separation not just from specific individuals, but from entire historical epochs of human development that will unfold during their absence from Earth. Advanced civilizations capable of achieving relativistic velocities would need to develop entirely new social structures and philosophical frameworks for dealing with the temporal consequences of high-speed travel that fragment communities across different reference frames and timelines. The energy requirements for accelerating spacecraft to relativistic velocities remain staggering, even when accounting for time dilation benefits, because the propulsion systems must still overcome relativistic mass increases and provide sustained acceleration over extended periods to reach the extreme velocities necessary for significant time dilation effects. Spacecraft designers would face unprecedented engineering challenges related to radiation shielding because relativistic velocities transform even tenuous interstellar hydrogen into high-energy particle beams capable of sterilizing biological organisms and destroying electronic systems through cumulative radiation damage. The navigation requirements for relativistic spacecraft become extraordinarily complex, because small course corrections demand enormous energy expenditures at extreme velocities, while the compressed time frame available for observations and decision-making eliminates the possibility of careful trajectory planning during the voyage itself. Communication with Earth becomes increasingly problematic at relativistic speeds due to extreme Doppler shifting that alters radio frequencies beyond the capability of conventional receivers, while the time dilation effects create additional complications for maintaining synchronized contact with ground-based mission controllers. The deceleration phase represents an equally challenging engineering problem, because relativistic spacecraft must somehow shed their enormous kinetic energy upon arriving at the destination stellar system, potentially requiring massive infrastructure investments at Alpha Centauri that exceed the resources available to any conceivable human expedition. Relativistic effects also impact the psychological experience of interstellar travel because the apparent shortening of distances and compression of time create perceptual changes that could disorient travellers accustomed to normal space-time relationships throughout their terrestrial lives. The fundamental asymmetry of relativistic travel means that while outbound journeys benefit from time dilation effects, return voyages would strand travellers even further in the future relative to their original departure point, making round-trip interstellar exploration essentially impossible for maintaining connections with specific individuals or cultural periods on Earth. What profound cosmic ballet has been unfolding for eons around our solar system, carrying stellar neighbours through space in a slow, gravitational waltz that reshapes our galactic neighbourhood over geological timescales. The Alpha Centauri system has served as our stellar neighbour for hundreds of millions of years, maintaining its position as the closest star system throughout vast epochs that witnessed the evolution of complex life on Earth, the rise and extinction of dinosaurs, and the entire evolutionary history leading to human consciousness and technological civilization. Stellar motions governed by the galactic rotation and gravitational interactions will eventually carry this familiar celestial companion away from our cosmic vicinity, following orbital trajectories around the Milky Way's centre that operate on timescales dwarfing all terrestrial experience and geological processes. In approximately 50,000 years, Alpha Centauri will begin its gradual retreat into deeper space as differential galactic rotation carries it along orbital paths that diverge from our solar system's trajectory through the galaxy, initiating a separation process that will unfold over hundreds of thousands of additional years. Other stars currently residing at greater distances are simultaneously approaching our solar system through their own galactic orbits, creating a constantly shifting stellar neighbourhood where cosmic proximity relationships change dramatically over extended timeframes. Gliese 445, a red dwarf star currently located 14 light-years away, will become our closest stellar neighbour in approximately 1 million years, as its galactic orbit brings it within less than 4 light-years of our solar system, potentially closer than Alpha Centauri's current position. The cosmic neighbourhood shifts continuously on timescales that completely dwarf human civilization, individual lifetimes, and even the entire span of recorded history, operating according to gravitational mechanics and galactic dynamics that persist unchanged across millions of years, while human societies rise and fall in cosmic insignificance. These stellar motions result from the complex interplay between galactic rotation, gravitational perturbations from massive stellar objects, and the overall expansion of space itself, creating a dynamic environment where apparent stellar positions change gradually but relentlessly over astronomical timeframes. Proper motion measurements reveal that individual stars move through space at velocities typically ranging from dozens to hundreds of kilometers per second relative to our solar system, though these seemingly rapid speeds translate into barely perceptible angular changes when observed from Earth across human lifetimes. The local standard of rest represents the average motion of stars in our galactic neighbourhood as they orbit the Milky Way's centre, providing a reference frame for understanding how individual stellar systems deviate from typical galactic orbital velocities through their interactions with gas clouds, stellar clusters, and gravitational perturbations. Barnard's star exhibits the largest known proper motion of any stellar object, racing across our sky at over 10 arcseconds per year as it approaches our solar system at such high relative velocity that it will pass within approximately 6 light-years of Earth in roughly 10,000 years before continuing its journey deeper into our galactic region. Wolf 359 and several other nearby red dwarf systems follow similar orbital trajectories that will bring them closer to our solar system over the next few 100,000 years, while simultaneously carrying other familiar stellar neighbours beyond practical observation distances. The three-dimensional structure of our local stellar environment resembles a constantly evolving bubble of space containing roughly 1,000 star systems within a 50 light-year radius, though this population changes continuously as stellar orbits carry objects into and out of our cosmic vicinity. Stellar associations and moving groups represent collections of stars that share similar ages, compositions, and galactic motions, indicating common origins in ancient star-forming regions that have since dispersed throughout our galactic neighbourhood through differential orbital mechanics. The Hyades and Pleiades clusters provide examples of stellar groups whose members are gradually separating due to galactic tidal forces and individual stellar velocities, demonstrating how even gravitationally bound systems eventually dissolve into the general stellar population over sufficient time periods. What if humanity abandoned the quest for impossible velocities and instead embraced the profound patience required for truly multi-generational voyages across the cosmic void? Perhaps the answer to interstellar exploration lies not in achieving tremendous speed, but in accepting the extended timeframes that interstellar distances naturally impose, designing self-sustaining habitats capable of supporting human communities during centuries-long journeys through the emptiness between stellar systems. These massive generation ships would need to carry thousands of humans along with complete ecosystems, manufacturing capabilities, and cultural preservation systems that could maintain technological civilization throughout voyages spanning dozens of human lifetimes. Self-sustaining habitats carrying entire populations across the void would represent the ultimate expression of human engineering and social organization, creating artificial worlds capable of supporting complex societies while traveling through interstellar space for periods longer than recorded human history. Multiple generations would be born, mature, reproduce, age, and die during these epic journeys without ever setting foot on planetary surfaces or breathing natural atmospheres, creating unique cultures adapted to life aboard spacecraft that become permanent homes rather than temporary transportation vehicles. The original travelers who departed Earth would never witness their destination, because the journey itself would outlast their natural lifespans by enormous factors, requiring unprecedented social structures for maintaining mission continuity across generational transitions that could span centuries or millennia. The great-great-grandchildren of the original voyagers would finally see Alpha Centauri grow bright in their forward viewports as their ancestral ship approached the destination stellar system, carrying genetic heritage and cultural memories from a home world they had never seen, except through archived recordings and historical documents. These voyagers would not be travelling to a specific destination in any conventional sense, but rather becoming explorers by birth, inheriting cosmic journeys as their fundamental life circumstance, rather than choosing adventure through personal decision-making processes. Generation ship societies would need to develop entirely new forms of governance, economics, education, and cultural continuity adapted to the unique constraints of permanent spaceflight where external resources remain completely inaccessible, and internal recycling becomes essential for survival. The psychological challenges facing generation ship populations would include maintaining motivation for missions whose completion lies beyond any individual's lifespan, while preserving technical knowledge and cultural values across generational transitions that could fundamentally alter social priorities and technological capabilities. Advanced closed-loop ecological systems would need to support complete food production, atmosphere recycling, water purification, and waste processing throughout journeys lasting centuries, requiring biological and technological redundancy far exceeding anything achieved in terrestrial applications or short-duration space missions. Genetic diversity becomes crucial for generation ship populations because small founding groups could suffer from inbreeding depression and genetic bottlenecks that compromise population viability over the extended timeframes required for interstellar travel using conventional propulsion technologies. Education systems aboard generation ships must transmit not only basic literacy and numeracy, but also specialized technical knowledge required for spacecraft maintenance, life support operations, and mission continuation across generations that may lose direct connection to the original departure motivations and scientific objectives. Social stratification and political conflicts could develop within generation ship communities as populations adapt to their unique circumstances, potentially leading to civil disorders or mission abandonments that would strand entire populations in interstellar space without hope of rescue or external assistance. The technological infrastructure aboard generation ships must remain operational and repairable, using only onboard resources throughout journeys exceeding the design lifetime of any terrestrial manufacturing systems, demanding unprecedented reliability and maintainability standards for critical life support and propulsion systems. How did the seemingly simple act of measuring angles smaller than a virus fundamentally revolutionize humanity's understanding of our place within an incomprehensibly vast cosmos? Understanding Alpha Centauri's true distance transformed astronomy from a qualitative science focused on cataloguing celestial appearances into a quantitative discipline, capable of determining actual physical properties of stars, planets, and galactic structures throughout the observable universe. We learned to measure the unmeasurable through ingenious applications of basic geometry and trigonometry, developing techniques that could quantify distances so enormous they exceeded human comprehension, while establishing the fundamental spatial framework necessary for all subsequent astronomical discoveries. Each parallax measurement represents a victory of precision over cosmic vastness, demonstrating humanity's remarkable ability to extract meaningful information from angular displacements thousands of times smaller than the limits of human visual perception, using nothing more than careful observations and mathematical analysis. These distance measurements remind us constantly that the universe operates on scales far larger and stranger than intuition suggests, revealing cosmic architecture where our entire solar system occupies an essentially negligible volume within galactic structures spanning hundreds of thousands of light years across space and billions of years through time. In measuring how far Alpha Centauri actually lies from our terrestrial home, we simultaneously discovered how remarkably small we truly are within a cosmic hierarchy that extends from subatomic particles through planetary systems to galactic superclusters containing billions of individual galaxies scattered across observable space. The parallax measurements that began with Henderson and Bessel established the first reliable distance scale for astronomical objects beyond our solar system, providing calibration standards that enabled subsequent discoveries including Cepheid variable stars, type Ear supernovae, and other cosmic distance indicators used to map the large-scale structure of the universe. Modern space-based astrometry missions like Gaia extend these pioneering measurements to unprecedented precision levels, while surveying billions of stellar targets throughout our galactic neighbourhood, creating three-dimensional maps of stellar positions and motions that reveal the detailed structure and evolutionary history of the Milky Way galaxy. The technological progression from ground-based visual observations through photographic surveys to space-based digital detectors demonstrates humanity's persistent drive to push measurement capabilities toward fundamental physical limitations imposed by quantum mechanics and electromagnetic radiation properties. Parallax astronomy exemplifies how scientific breakthroughs often result from incremental improvements in measurement precision, rather than revolutionary theoretical insights, requiring patience and dedication across multiple generations of researchers who refine techniques and accumulate observations over extended timeframes. The distance measurements to Alpha Centauri and other nearby stars provided essential observational evidence supporting heliocentric cosmology, while simultaneously revealing that stellar distances exceeded contemporary estimates by enormous factors that challenged existing theories about cosmic structure and organization. These measurements established astronomy as a mature physical science, capable of making testable predictions and quantitative comparisons between theoretical models and empirical observations, transitioning the field from philosophical speculation toward rigorous scientific methodology based on precise measurements and mathematical analysis. The philosophical implications of stellar distance measurements extend far beyond astronomy, because they fundamentally altered humanity's perception of our cosmic significance and the spatial scales governing natural phenomena throughout the observable universe. Knowledge of interstellar distances enables calculation of stellar luminosities, masses, and evolutionary timescales that provide insights into the physical processes governing nuclear fusion, gravitational dynamics, and the chemical evolution of matter from primordial hydrogen and helium toward the complex elements necessary for planetary formation and biological processes. What profound journey have we taken together through the cosmic scales that separate us from our nearest stellar companion? And how does this knowledge transform our understanding of both distance and wonder? As we reach the end of our exploration into Alpha Centauri's true remoteness, we find ourselves changed by the perspective these measurements provide, humbled by the distances that dwarf human imagination, while simultaneously inspired by our species' remarkable ability to quantify the seemingly infinite through careful observation and mathematical precision. The 4.37 light-years separating us from our closest stellar neighbours represents far more than simple measurement, because it embodies humanity's greatest triumph over cosmic ignorance, demonstrating how patient scientific inquiry can unlock secrets hidden within angular displacements smaller than viral particles observed across interstellar voids. Tonight, as you prepare for rest and your thoughts drift toward the southern sky where Alpha Centauri shines with ancient light, consider how every photon entering your eyes began its journey years ago, when global circumstances differed dramatically from current conditions, carrying information about stellar processes occurring in cosmic laboratories we may never visit personally. These measurements reveal not only astronomical distances, but also the fundamental loneliness characterizing our cosmic situation, where even the closest possible destinations remain separated by gulfs requiring decades or centuries to cross using any conceivable transportation technology. Yet within this isolation lies profound beauty, because the same physical laws that create these impossible distances also enable the electromagnetic radiation that connects us across space and time, allowing stellar light to bridge cosmic separations that spacecraft cannot traverse. The precision achieved by modern astrometry missions represents one of humanity's greatest intellectual achievements, pushing measurement capabilities into realms where quantum uncertainty and relativistic effects become significant factors in determining cosmic distances with accuracies that approach fundamental physical limitations. If this gentle journey through cosmic measurement has sparked your curiosity about the scales governing our universe, your quiet like or soft subscribe would mean more than you might imagine, supporting these contemplative explorations of scientific wonder that connect human consciousness to cosmic vastness done through mathematics and patient observation. Perhaps you might share in the comments below where you experienced this cosmic meditation, whether from bustling cities where light pollution obscures Alpha Centauri, or from dark rural locations where our stellar neighbour shines clearly against the backdrop of more distant stars scattered throughout our galactic neighbourhood. Your presence here, your willingness to contemplate these enormous scales and precise measurements, creates a community of minds reaching across terrestrial distances to share appreciation for the cosmic architecture that surrounds and dwarfs our planetary home, while simultaneously celebrating the remarkable capabilities of human intelligence and scientific methodology. Tonight, as you drift towards sleep, remember that the light touching your eyes from Alpha Centauri began its journey years ago, carrying with it the quiet message that even the closest stars remain impossibly, beautifully distant, and that in measuring this distance, we measure our own cosmic loneliness alongside our remarkable ability to reach across the void with nothing but mathematics and wonder.